Good morning. This is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. Today we will discuss one topic called stability analysis. It is the part 2 of this topic, and this topic comes in computational fluid dynamics for 6th semester mechanical engineering students. Now the von Neumann stability analysis. So this is the most commonly used procedure for analyzing the stability of the finite difference equations. So a solution of the finite difference equation is expanded in Fourier series. So an example of Fourier series is given this equation. This is un of x is equal to sum of minus n to capital N, minus n to plus n cn e power I theta x. So this is an example of Fourier series. This the solution is expanded in the form of Fourier series. So the decay or growth of amplification factor indicates whether or not the numerical algorithm is stable. So in this analysis, first what we'll do, we'll find what is called the amplification factor. So the amplification factor is given like this: un plus 1 by un is equal to amplification factor. Now whether this amplification factor is decaying with respect to as we move along with the time steps, or whether it is going. Based on that, we'll come to conclude that the numerical algorithm that we have written is stable or not. So the effect of so in von Neumann stability analysis, in the previous section we have seen that perturbation analysis. In that, the effect of boundary conditions is included. Now, in this von Neumann stability analysis, the effect of boundary conditions is not included. Now, here the condition is that the finite difference equation must be a linear one. Okay, in for analyzing using the von Neumann procedure, the FDE, the finite difference equation, must be a linear one. So why we are taking linear is, if it is a linear equation, what we can do, we can investigate only one component of the Fourier series. We don't have to analyze the entire Fourier series. We can analyze only one component of the Fourier series if the FDE is a linear one. So that is the why what we are doing, we are giving a constraint that the linear FDE must be a linear one for using the von Neumann stability analysis. So this is the one element of the Fourier series, and you can see here this is un and u power n e power I theta I. So this is the one element that we are going to investigate. This is one element of the Fourier series that which we are going to investigate in von Neumann stability analysis. So we'll see. But if it is a non-linear equation, so if the condition for stability and von Neumann stability analysis is the FDE must be linear. Now, if it is a non-linear equation, can't we use the von Neumann stability analysis? Yes, we can use it. How to use it? We have to locally linearize the FDE. By locally linearizing the FDE, we can analyze the stability of that equation using the von Neumann stability analysis. But what happens is, the result that we get, or the stability criteria that we will get, is satisfied only in that locality where it is linearized. So the actual stability requirement for the entire equation may be different. Okay, so because we are for a non-linear equation, we are locally linearizing the equation and analyzing the doing the von Neumann analysis and finding the stability requirement, and that requirement is satisfied only locally. So what happens is, for the entire equation, the stability requirement will be different. Then why we have to do von Neumann stability analysis? Because it is not giving the stability requirement for the entire equation. It is giving stability requirement only for the local area or local region where we linearized the equation. So the reason is that this it will give us it will provide us very useful information for stability requirements. So for locally we'll get stability requirement. Based on that we can find out the stability requirement for the entire equation. So that is why what we do, we go for the von Neumann stability analysis even for the non-linear equations. Now what is the procedure for von Neumann stability analysis? So here in this diagram it is showing the nodal positions of the FTCS, the forward in time, central in space. This is one explicit method, and in this explicit method how the nodes are there. So this is the time n. So when the time n is there, we know the value of I minus 1 and I plus 1th node. Now using the information of these nodes, what we are doing, at n plus 1th time interval, we are finding the value of the node I. So this is the unknown and this is the known values. Now here, if we the Fourier component that, as I have already discussed, the Fourier component that we are assuming is UIN, and it is assumed as UIN is equal to U power n e power I p delta x I. Now in this, what is UN, what is I, what is p, what is delta x, what is I, small I. So these things we have to see. Now the I, here the small I is used for the space. The small I, generally the imaginary number small I will be used, but here the small I is already allocated to the space coordinate. That's why what we are doing for the imaginary term, we are taking a capital I which is equal to root of minus 1. Now U power n is the amplitude at nth time interval. So U power n is the amplitude of the equation at at nth interval of time, or at nth time step. So we have nth time step and n plus 1th time step. So U power n means it is the amplitude at nth time step. Now what is P? P is the wave number. Okay, here P is there, capital P in this equation. This P is the wave number, and that P is equal to 2 pi by lambda x. Okay, in x direction P is equal to 2 pi by lambda x. Now what is this lambda x? Lambda x is nothing but the wavelength of the equation. Now if I want, we have the UI at nth level. So if I want to find the Fourier component at n plus 1th time and n plus 1th time and ith location. So for this, what I have to do, I have to take amplitude at n plus 1th time interval, and I is common, P is common, delta x is common, and ith interval. So the I in space it is I, so we have taken as it is. Now if I want to take at I plus 1, say suppose it I plus 1th location, we have I minus 1 location and I plus 1 location. For these two cases, what will be the Fourier component UI plus or minus 1 power n. Now this is equal to UIN. So the amplitude at time interval n, at time n, time step n, time step. Now e power capital I is common, and P is constant, and delta x is increment, that is also constant. Now here the time interval, the space, in the space coordinate is I here because the suffix is I, and now here the space coordinate is I plus or minus 1. For I plus 1 I will get I plus 1 here, for I minus 1 I will get I minus 1 here. So now if I substitute the P delta x as the phase angle, if I substitute this P delta x, I have P delta x here. If I substitute P delta x as the phase angle theta, then what will happen? This will become UIN U power n e power I theta. In place of Px, I will get theta. So e power I theta I, this we will get. So if similarly for n plus 1th time, if I want to know the amplitude at n plus 1th interval of time and e power I theta I. So if I want this I minus plus or minus 1, I plus or minus 1 location at I plus or minus 1 location, then it will be the amplitude at time interval n and e power I theta and I plus or minus 1. So we have these three equations and we'll use these three equations and do our stability analysis. Now these are the three equations that we have already derived. Now we'll proceed with the stability analysis. Now consider this equation. This is a diffusion equation, and for this equation what we are doing, we are using explicit finite difference formulation. Now the explicit finite difference formulation is forward differentiation in time and central differentiation in space. Okay, the forward differentiating in time and central differentiating in space. So it is called FTCS formulation. Now this FTCS formulation is second order accurate in space and first order accurate in time. Now if I do the FTCS for this, what will happen to this? It will become u power ui n plus 1. So it is a central difference. So for this I want a central difference, and that central difference is between n plus 1 and nth location. Okay, it is a n plus 1 and n, and the ui n plus 1 minus ui power n by delta t. So this is a central difference. Now this is a forward difference. So the forward difference using time. So this is the known one, this is the unknown one. So we are going one step forward. So it is called forward. Now here this is the location where we are at. We are at a location I, and we are using I plus 1th location and I minus 1th location. So it is called a central differencing central difference. Okay. Now this in space it is central difference, and in time it is a forward difference. Now if I use this, okay, and I have ui n plus 1, this is the value of ui n plus 1, the value of ui power n is there, and ui plus 1 power n, ui minus 1 power n. So if I substitute all these values in this equation, what will happen? I will get this kind of equation. Okay, I will get this kind of equation. Now in this equation, this d, I am giving a number, diffusion number. So what is this diffusion number? I am taking this delta t this side. If I take this delta t this side, it will be alpha delta t by delta x whole square. So this is the common factor. So this common factor is given as d. So if I give alpha delta t by delta x whole square as d, what will happen? I will remain here with u I power n plus 1 minus ui n d into this term will be there. So what I am doing is I am taking this ui n this side. So it will become this equation. So this is the transformed equation of the FTCS equation. The FTCS equation is transformed into this equation using the Fourier terms here. Okay, the one component of the Fourier terms we are taking, and we are transforming this FTCS equation into this form. Now, what is the value of ui power n? The ui power n is there, ui power n plus 1 is there, ui plus 1 power n is there, ui power n is there, ui minus 1 power n is there. All these values I am substituting here, and the equation will be transformed like this. So there is nothing difficult here. I am taking ui power n value and substituting here, and I am taking ui plus 1th value and substituting in this place, and ui plus 1 power n and substituting here, ui minus power n and substituting here. Like this I am taking the values here and substituting. Now if I substitute all these things, the equation will be in the form of the amplitude. So we need the G is nothing but the amplification factor. This amplification factor, how it is, whether it is decaying or increasing. That is what we have to see. So for that, what we are doing, we are transforming this for FTCS equation into the form which have the amplification factor. Okay, now what we'll do, we'll take this equation and simplify. So this is the equation that we have derived. In this, is there any common term for eliminating? So here, this is a common term, this is common term, here also I can eliminate, this is common term, here also I can eliminate. So if I simplify that, what will happen? I will get this equation. Okay, this is the equation that we are getting. Now, is there any other thing modification that we can do? E power I theta and e power minus I theta is there. So, and here u power n. Okay, u power n is common in all this. I have taken u power n outside. So, u power n plus 1 by u power n. That will be the g value. Now, here e power I theta and e power minus I theta. So what is e power I theta plus e power minus I theta? It is nothing but cos theta. So e power I theta plus e power minus I theta by 2 is nothing but cos theta. If I substitute that one here, what will happen? The equation will become u power n plus 1 is equal to u power n into 1 plus 2 d cos theta minus 1. Okay. So I am substituting here in this place. What I am doing, I am substituting 2 cos theta. I have substituted that one here and taken 2 outside. What will happen? 2d into cos theta minus 1. Now, this, as we have already discussed, u power n plus 1 by un is nothing but the amplification factor. So, this is the equation that we have arrived at. Now, what is the value of this amplification factor? The amplification factor, the modulus of this amplification factor must be less than or equal to 1 in order that the solution is a stable one. Okay. So, to get a stable one, the amplification factor must be, the modulus of the amplification factor must be less than or equal to 1. So, here what is the amplification factor? This is the amplification factor. So, apply the modulus for this amplification factor and see how it changes. Now, if this equation, okay, this equation is satisfied for all values of theta. Okay, this equation is satisfied for all values of theta. Say suppose if I take this theta varies from 0 to 1. Okay, all values of theta, cos theta varies from 0 to 1. So whatever the value may be, it will be less than or equal to 1. So what we are saying, for all values of theta, this is satisfied. Now, if here we have modulus. When we have modulus, we have two values. One is less than or equal to 1 and another one is greater than or equal to minus 1. Now, the first one, it is satisfied for all values of theta. Now, for the second one, when it is greater than or equal to minus 1, we have to see what is the condition. So, we have to derive what is the condition. Now, here, this minus 1 is there. If I take this minus 1 here, it will be plus 2. So, the 2 here are there. If I cancel, it will be like this. Now, this equation, what will happen to this equation? I want to find what is the value of D for the stability criteria. Now, here I am substituting 1 minus cos theta, maximum value of 1 minus cos theta. So, what is the maximum value of 1 minus cos theta? It is 2, because cos theta value, when it is minus 1, then the theta, when cos theta is minus 1, the value will be maximum. So, it is 1 minus cos theta is maximum value is 2. If I substitute that 2 in this place, what will happen? 1 minus 2d is greater than or equal to 0. That means d is less than or equal to half. So, the stability criteria is when d is less than or equal to half, the diffusion number d is less than or equal to half, then only this is a stable one. Okay. Now, this is what we have defined as the diffusion number. The diffusion number is d, and d is equal to alpha delta t by delta x whole square. Now if this alpha delta t by delta x whole square is equal to half, what happens to the relationship between the interval in space and interval in time? So this is the interval in time step. So the time step, how should be the time step, and how should be the space, space marching step, such that the condition of stability is arrived. So here alpha delta t by delta x whole square is equal to half. So if that is the case, then delta t is equal to 1 by 2 alpha into delta x whole square. So this delta x, if delta x is very small, then delta t is can be very small. If delta x is very high, the delta t also can be very high. So this is, in this way, this can be used. So we'll see how this amplification factor, here the amplification factor is there for different values of d, how this amplification factor varies. So here for different values of theta, theta is varying from 0 to 360. So theta is varying from 0 to 360, and the d for different values of this diffusion number, how the amplification factor is varying. So if d is equal to 0.25, say suppose, because here the d is less than or equal to half, that is what is taken. So if it is less than, if it is equal to half, we will have a stable condition. If it is more than half, it will have an unstable condition, because it is varying from minus to positive. And if it is less than half, it will be further stable. So the stability condition is the d value must be less than or equal to half. When in such case only this the FTCS method that we applied for the diffusion equation can be a stable one. So this is about the von Neumann stability analysis. So there is something called error analysis. What we have seen is a stability analysis. Now we will see what is error analysis. So suppose if the lower order term in the truncation error is of order 1, okay, the truncation error or in the lowest order is 1, then it is called first order accurate method. If the lowest order is 2, then we can say that the second order accurate method. So for this equation, diffusion equation, this is the first order accurate method and this is the second order accurate method. Okay, so this is the first order accurate method and this is the second order accurate method. So what we have to see is there will be some errors and how these errors are influencing. So the first order accurate method, whatever error we will get is termed as dissipation error. Okay, the first order accurate method, whatever error we will get is a dissipation error. In second order accurate method, whatever error we will get is a dispersion error. This is a dissipation error and this is a dispersion error. Now how this dissipation error and dispersion error are physically, if you want to see, you see here. So the first order accurate method, here this is the first order accurate method and this is the second order accurate method. Now this the first order accurate method will decrease the gradient within solution domain. Okay, the first order, the dissipation errors will decrease the gradients. Okay, the slope is decreasing. This is the actual slope and the slope is reduced. So here initially this is the accurate one and this is the first order one. The slope got reduced. So there is an decrease in amplitude of the wave. So initially the actual value is the amplitude is like this, but the first order value, the amplitude is less, the amplitude is decreased. Now coming to the second order accurate method, it is called dispersion error, as I already said. Now this dispersion errors, what it will do? It will give some oscillation in the solution. So you can see here, here it is going down, it is going negative values and coming to positive values. So there is some oscillation in the solution. So the second order accurate method, whatever errors you get, they will give some oscillation in the solution. So this is about the error analysis. Now there is something called modified equation. Okay, what is this modified equation? To determine the dominant error term of the finite difference equation, the Taylor series expansions are substituted back into the FDE finite difference equation, and after some algebraic manipulation, we obtain modified equation. So what is this modified equation? We have the finite difference equation and we are substituting the Taylor series expansions into the finite difference equation, and we are modifying that algebraically, and the final equation what we get is the modified equation. Okay, so the same equation that what we have seen previously, that the same equation will take. So this is the equation that we have, and for this equation what we have to do, we have to apply the finite difference formulation. So if I do the first order accurate finite difference formulation, this will be the first order finite difference formulation. So this is forward and this is also forward. First this is forward in space and this is also forward in, this is forward in space and forward in time. So it is a first order accurate method. Now this example will show the dominant error terms in this method and their relationship to dissipation and dispersion error. So we have already seen in error analysis there are two types of errors. One is the dispersion error and the other one is a dissipation error. So if I formulate the modified equation, if I find the modified equation for this finite difference equation, what it will do, it will give us any relationship between this dissipation error or dispersion errors. Now this is the finite difference formulation that we have. Now what I have to do, I have to substitute the expansions for uin plus 1, uin and uin minus 1. So what is this uin plus 1? So if first what I am doing is I am transforming this into a normal equation. When I am taking this delta x here and putting here, and in this equation I am substituting the Fourier expansions. So this is the Fourier expansion for uin plus 1. So uin plus 1 is equal to uin dou u by dou x into delta t, like that it will go. So this is the, if I truncate the fourth order term, it is order of accuracy is 4. Similarly I can find for ui minus 1 n, ui minus 1 n, the fourth order accurate equation is like this. So if I substitute this equation and this equation back into this finite difference equation, what will happen to my finite difference equation? So the finite difference equation will be like this. So okay, what I am doing here, I am taking the value of ui n plus 1 and substituting here. I am taking the value of ui I minus 1 n and substituting in this place. So if I substitute like that, ui power n, this entire equation will come here, is equal to, this will be as it is, minus a into delta t by delta x, this will be there here like that, and ui power n, this is as it is, ui minus power n, in that place I am putting this equation. So this is the equation that we got by substituting the Fourier expansion of ui power n plus 1 and ui minus 1 power n into this finite difference formulation. So what I have to do now, I have to do some algebraic simplification of this equation. So this is the equation that we have. So how to do the algebraic simplification? So here this is ui power n and this is ui power n. You can both are same. equal, so we can eliminate this term. And here also u I power n is there, and here also u I power n is there. I can eliminate that term as well. So if I eliminate those two, I will end up with this equation. Now in this equation, what I can do, I can take out delta t common out of this bracket, and I can take delta x common out of this bracket. If I take delta t here, so this delta t will get cancelled. Here it will be 1, here it will be 2, and here it will be third order accurate. And here delta x will be the out. This it will become 1, and this will become 2, and it will become third order accurate. Okay. So if I do like that, it will be like this. Now here delta t is there, here delta t is there, I can eliminate. Here delta x is there and delta x is there, I can eliminate them. So if I eliminate that, what will happen is I will get this equation. So this is the equation that I am getting finally. So this is the modified equation. This is the modified equation of this. This is the equation that we started with. This is the diffusion equation that we have taken. We have given the we have find out the Fourier formulation, first order Fourier formulation, and substituted back the Fourier's expansion for ui power n plus 1 and ui minus 1 power n. If I substitute that and simplified, and this is the modified equation that I got. Okay, this is the modified equation. And here if I compare this, this is there, this equation, and this one is as it is. So the remaining terms are our errors. Now taking the time derivative of the partial differential equation. So this is the partial differential equation that we have. If I do the time derivative, if I derive this with the time, so what will happen? Dou square u by dou t square and minus a dou u by dou x, dou by dou t of dou u by dou x I will get. So if I now here these two can be interchanged because this is a differentiation. So what I am doing, I am interchanging this. So if I interchange that, dou by dou x of dou u by dou t will be there. Now dou u by dou t is already known here. So the dou u by dou t is minus a into dou u by dou x. I am substituting that one here. If I substitute that here, what will happen? It will be equal to minus a square into dou square u by dou x square. So dou square u by dou t square is equal to minus minus a square into dou square u by dou x square. So this value I can substitute in this place. Okay, here I can substitute dou square u by the value of dou square u by dou t square, and that will be this. Similarly, I have to find what is dou cube u by dou t cube. So if I further differentiate this time, if I take the time derivative of this again, what I will get? I will get simply dou cube u by dou t cube is equal to minus a square dou by dou t of dou square u by dou x square. If I simplify this, if I substitute back in this equation, here I am substituting dou cube u by dou t cube and dou square u by dou t square values. If I substitute, this is the dou square u by dou t square value, and this is dou cube u by dou t cube value. So if these two values, if I substitute in this equation, what I will get? I will get dou u by dou t minus this and etc. etc. Now this is the equation that we got. Now in this equation, what is happening here? This is the error term of this first order accurate method is clearly indicating that the second term on the right hand side is being dominating the error. So which one is having the maximum value? Here for different c values, this will have a dominant effect on this. Here it is power 2 is there, and here it is only power 1. So this term will have a dominating effect on the solution, okay, on the stability of this solution. So the coefficient of dou square u by dou x square, the dou square u by dou x square is termed as artificial viscosity. It is not the physical property of the fluid. It is introduced because of the approximation, because of the approximation of the partial differential equation. So this partial differential equation we have approximated, and this is the error. Because of this approximation, what we are getting is a term called as artificial viscosity. Now what is this artificial viscosity? Alpha E is equal to, it is equal to A into delta x by 2 into 1 minus C. A into delta x by 2 into 1 minus C. This is the artificial viscosity term in this equation. Now this artificial viscosity, if C is equal to 1, the artificial viscosity is equal to 0. If artificial viscosity is 0, then the solution is an accurate one, because you can see here it will be 0 and here it will be 0. So if all the terms are 0, then this is our initial partial differential equation, and finally we are getting the same. So the solution that we get is an exact solution. Now the effect of this artificial viscosity is to dissipate the error in the solution. Okay, it will dissipate the error in the solution. As a result, the gradients are reduced. So the same thing, we have seen that this is the exact solution, and the first order accurate solution is like this. So in the first order accurate solution, what is happening? We have already discussed, the amplitude is reducing. So this is the amplitude and this is the new amplitude in first order accurate method. So the amplitude is reduced, the solution, the error in the solution is dissipated, and the gradients are getting reduced. So this is about the artificial viscosity. So in this lecture, what we have seen, we have discussed about what is von Neumann stability analysis, and why, when we can use von Neumann stability analysis, why we have to use von Neumann stability analysis. And then we have seen what are the errors, the dissipation error, error analysis, dissipation and error, and dispersion error. Then we have seen the modified equation, in how to get, why we have to see modified equation, how these errors are related, the dissipation error or dispersion error are related. For seeing that, we have seen the modified equation, and finally what we have seen in the modified equation for first order accurate one, we have got the artificial viscosity. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.